Welcome back, everyone, to the Deep Dive. Ready to explore some seriously cool robotics research.
Always up for a deep dive into cutting-edge robotics.
Okay, so today we're looking at this paper, EnerVerse Envisioning Embodied Future Space for Robotics Manipulation. Published, well, practically yesterday, January 1st, 2025.
Very new stuff, hot off the press.
Exactly. And our goal today is to really unpack their methods and results, especially how this EnerVerse framework can create these future spaces to help robots perform some really complicated tasks.
Sounds like a plan.
So to kick things off, can you maybe give us a quick rundown of the problem this research is trying to solve? What are some of the main challenges when it comes to robotic manipulation?
Well, you see, one of the toughest nuts to crack is getting robots to align instructions with what they actually observe, and then, of course, take the appropriate actions.
So it's kind of like they see, but they don't really understand.
Yeah, you could put it that way. Imagine trying to teach a robot to, say, bake a cake, right? You have the recipe, the robot sees all the ingredients, but actually translating that into the precise steps the robot needs to take, oh, that's a whole other ballgame.
I see. So it's not just about like see and do, it's about understanding the whole process, the logic behind it.
Absolutely. And then on top of that, we have this issue of data, or rather the lack of it. We're swimming in image data and text data, but when it comes to robots learning to move and manipulate objects in the real world, in 3D, that's where things get really scarce.
So data is a major bottleneck. That makes sense. So how does EnerVerse tackle these challenges?
It uses a pretty unique three-pronged approach. First, there's this thing called chunkwise autoregressive generation. Basically, it predicts what's going to happen next by breaking down complex actions into smaller, more manageable chunks.
Okay, so instead of trying to like predict the whole enchilada at once, it focuses on smaller bite-sized pieces.
Exactly, and this makes the learning process way more efficient. The second key component is what they call free anchor view space, or FAV for short. This gives robots flexible viewpoints, almost like having multiple virtual cameras floating around instead of being stuck with just one view.
Ah, so no more robot tunnel vision. They can actually see the world from different angles.
Precisely. This is super important for understanding 3D space, especially when a robot needs to interact with objects from different perspectives. And then, last but not least, to address that data problem we talked about, EnerVerse uses something called a data flywheel that integrates 4D Gaussian splatting. Basically, constantly refining and improving the training data.
4D Gaussian splatting. Now that sounds really complicated.
It is a bit on the technical side, but think of it this way. It allows them to build really detailed 3D representations of the environment, even from limited real-world data.
Ah, so they can then use these representations to like generate more data for training.
You got it. It's like a self-improving system, always getting better at understanding and representing the world.
Okay, that's starting to make more sense.
Uh,
Let's maybe unpack these individual components a bit more, starting with that chunk-wise autoregressive generation. What exactly does that mean? How does it actually work?
In simple terms, it means predicting the future by analyzing past events, but doing so in these manageable chunks. Let's say a robot's learning to, I don't know, fold laundry. Instead of trying to predict the whole process of folding a shirt in one go, it breaks it down. Picking up the shirt, laying it flat, holding the sleeves, you get the idea.
So it's like learning a dance routine. You master the individual steps first before putting them all together.
Exactly. Now, you might think remembering every single frame, that would be a lot of information, wouldn't it?
Yeah, it would be like trying to remember every single word in a book.
And that's where this sparse memory context mechanism comes in. Instead of remembering everything, it picks out a few key frames, the most informative ones. Makes it much more efficient.
Ah, so it's more like remembering the key takeaways, the main points.
Precisely. This way, the robot learns the underlying logic of a task, not just rote memorization.
So it's not just mimicry, it's about understanding the why behind the what.
Exactly. That's what makes this approach so powerful.
Fascinating stuff. Okay, let's move on to this free anchor view space. Why is it so crucial for robots?
Well, imagine trying to, say, assemble something in a really tight space, like under a car.
Right, you wouldn't be able to see much from just one angle.
Exactly. Traditional robots often rely on just a single camera, limiting their understanding of the 3D world around them. But with free anchor view, we can place virtual cameras anywhere, giving the robot a much broader perspective.
So it's like having multiple sets of eyes, seeing the task from all sides.
You got it. This is especially crucial for tasks that require a lot of spatial reasoning, like grasping objects in a cluttered space.
Right, because the robot needs to understand where everything is in relation to itself and to everything else.
Exactly. Multiple viewpoints mean the robot can better grasp, literally and figuratively, how objects relate to one another.
So it can essentially see around corners and behind objects.
Yeah.
That's incredible.
It really opens up a lot of possibilities for robot manipulation in more complex, realistic environments.
This is all very cool, but I'm still curious about this data flywheel you mentioned. Can you break that down for us a little more?
Sure. So, as we discussed, collecting real-world data to train robots is a pretty big headache. It takes ages and costs a fortune. So, how do we get enough data to train something as complex as EnerVerse? That's where this data flywheel comes in. They start by training a kind of basic version of the model in a simulation where you can easily generate tons of data from different viewpoints.
Ah, so they start with a virtual playground, get the model up and running.
Precisely. Once the model's got the basics down, they fine-tune it using real-world data, even if it's just from a single camera to start with.
Okay, but how do they go from single camera data to the multi-view data that Free Anchor View needs?
That's where the 4D Gaussian splatting comes in. Remember that. They use this technique to create a 3D reconstruction of the scene, even from that limited real-world data. And from that reconstruction, they can generate images from any viewpoint they want, effectively creating multi-view data.
So they're like bootstrapping the system. Simulated data, then real-world data, then this 4D magic to create multi-view data.
Exactly. And here's the kicker. This new multi-view data then gets fed back into the system, further training and refining EnerVerse.
So it's like a self-reinforcing cycle. More data, better model, even more data.
That's the idea. This data flywheel constantly bumps up the quality and diversity of the training data, bridging that gap between simulation and reality.
That's seriously ingenious. They basically built a system that can learn and improve on its own, getting better at understanding and interacting with the world.
You've summed it up perfectly.
Yeah.
Okay, so where were we? Ah, yes, the results. Did EnerVerse actually live up to the hype?
That's the million-dollar question, right? All this fancy tech is great, but does it actually work in practice?
Well, they put it through its paces, that's for sure. They used several benchmarks and data sets to see how it stacked up against existing methods.
Okay, like what?
Well, one of the key ones was RT1. It's designed to test a robot's ability to understand and follow instructions, complex ones.
So real-world type stuff, not just playing around in a simulation.
Yeah, RT1 involves tasks like placing objects, stacking blocks, even opening drawers. It really assesses how well a robot can generalize its learning to new situations.
That was pretty challenging. So how did EnerVerse do? Could it actually follow these instructions?
It did, and get this, it consistently outperformed a state-of-the-art method called Dynamic Crafter.
Oh, wow, I've heard of that one. That's a pretty powerful video generation model.
It is, but it doesn't have all the bells and whistles of EnerVerse. And the difference really showed, especially in these long-range tasks.
Long range means?
Tasks that involve a sequence of actions over a longer period. Not just simple pick and place, but like navigating a cluttered room or assembling something with multiple parts.
So stuff that requires more planning and reasoning, thinking several steps ahead.
Exactly. Dynamic crafters struggled with those, often got stuck or made illogical decisions. But EnerVerse, with its ability to envision those future spaces, it just sailed through those complex tasks.
It's like it had a roadmap, could see the end goal from the beginning.
In a way, yeah. The researchers were also very interested in how well EnerVerse handled tasks that require a strong understanding of 3D spatial relationships, where things are in space.
Which makes sense. Robots need that 3D awareness to operate effectively in the real world.
Absolutely. And that's where the multi-view consistency of EnerVerse really shone. Remember those free anchor views? Well, EnerVerse generated videos from multiple viewpoints, and they were incredibly consistent with each other.
So like no matter which angle the robot was looking from, it had a stable and reliable view of the world.
Exactly. It wasn't getting confused or disoriented. And this translated to really impressive results. Smooth, accurate movements, a clear understanding of how objects relate to each other in 3D.
It sounds like they've really nailed this multi-view perception and generation. That's a big deal for robotics.
It is. And what's even more exciting is that EnerVerse didn't need a ridiculous amount of training data to achieve all this.
Right, because the data is a major bottleneck in robotics research.
Yeah.
So how do they manage to pull this off with limited data?
That's the beauty of that data flywheel we talked about. Combining simulated data, real-world data, and that clever 4D Gaussian splatting technique. It's like a self-bootstrapping system.
So they start with a little bit of real-world data, use that to build a 3D model, then use that model to make more data, which then feeds back into the model.
You got it. It's a really elegant solution to this data problem, and it seems to work incredibly well.
Okay, all very impressive. But how does EnerVerse perform in the real world, outside of these controlled tests? Did they actually put it on a real robot?
They did. They conducted experiments using two different robot platforms, the Agibot A2W and the Agibot A2D. The real deal, designed for industrial settings.
Okay, now we're talking. What kind of real-world task did they throw at it?
One task involved placing blocks into specific compartments, but here's the catch. It was on a foam work table. The foam and the table were visually very similar, so super tricky for a robot to differentiate.
Even for us humans, that would be a pain.
You'd think so, right? But EnerVerse aced it, placed the blocks with amazing accuracy, really shows how well it can handle fine-grained tasks, even in tough conditions.
Wow.
Anything else? Yeah, they also had it sort of bunch of transparent plastic objects measuring cups, plates, that sort of thing.
Ah, transparency. That's always a challenge for robots. Hard to perceive shapes and boundaries when you can see through things.
Exactly.
Ah,
But guess what? The multi-view capabilities of EnerVerse came to the rescue again. Having those multiple viewpoints allowed the robot to see past the transparency and sort those objects with no problem.
that's amazing. They basically gave the robot X-ray vision. So it sounds like EnerVerse is not just a theoretical concept. It actually works in the real world.
The real-world experiments were really the icing on the cake. They showed just how robust and adaptable this framework is.
Okay, so they've got the results. They've shown it works in the real world, but did they dig any deeper? Try to figure out why it works so well.
Oh, they definitely did. The further studies section of the paper is where things get really interesting. They did all sorts of cool experiments to really dissect the inner workings of EnerVerse.
Okay, spill the beans. What did they find?
Well, for one, they confirmed just how crucial that sparse memory mechanism is. Remember, the part that selectively chooses what to remember? They found that without it, both the video generation and the robot's policy learning tanked.
So it's not just a memory-saving trick. It's fundamental to how the system learns and reasons.
You got it. Another fascinating finding was about the role of pre-training. They realized that just training the whole system from scratch, even with loads of data, wasn't very effective.
So there's more to it than just data, data, data.
Exactly. The best results came when they first pre-trained the video generation part of the system on a massive data set of general videos.
It's like giving the robot a basic education about the world before teaching it specific skills.
Perfect analogy. And finally, they did some really neat analysis of the attention maps in the policy head of the system.
Attention maps. Refresh my memory. What are those again?
They basically show you which parts of the input data the model is focusing on when it makes decisions, like peeking into the robot's brain.
Ah, right. So they were trying to figure out how the policy head, the part that decides what actions to take, was using both the sparse memory and the generated future frames.
Exactly. How it integrates information from the past and the future to make decisions in the present. And what they saw was fascinating. The robot was dynamically shifting its focus between the past and the future depending on the task at hand.
So not just blindly following a script, but actually reasoning and adapting based on what it has learned and what it predicts will happen.
Exactly. This level of flexibility and adaptability is really remarkable. It goes beyond anything we've seen in earlier robotic systems.
Well, this has been an incredibly insightful deep dive. It's clear that this research is a real game changer. What implications do you think this could have for different industries and applications?
The potential is huge. Manufacturing, logistics, healthcare, all these fields could be revolutionized by robots that can reason, plan, and adapt like this. But for now, I think the main takeaway is that EnerVerse represents a major leap forward in our understanding of how robots can learn and interact with the world.
I completely agree. And for any of our listeners who are eager to dig deeper into the nitty-gritty details, we'll be sure to include a link to the full paper in the show notes.
Absolutely. It's well worth a read.
All right, so I think we've covered just about everything on EnerVerse. Any other thoughts before we wrap things up?
Yeah, it's exciting to think about where this kind of research could lead,
Right. We're not just talking about robots that can follow instructions anymore. We're talking about robots that can actually understand what they're doing.
Exactly. And that's what's so groundbreaking about this work. They haven't just created a new algorithm or a new piece of hardware. They created a whole new way of thinking about robotic manipulation.
And that opens up a ton of possibilities, doesn't it?
Oh, absolutely. I mean, imagine a world where robots can not only perform tasks, but can actually learn and adapt on the fly. Think about the impact that could have on manufacturing, logistics, healthcare, you name it.
No more robots just stuck in cages doing repetitive tasks.
Mm,
They could be out in the world, collaborating with humans, solving problems in real time.
precisely. And that's what I find so inspiring about this research. It's not just about making robots more efficient, it's about making them more intelligent, more capable, more human-like in a way.
It's almost like they're blurring the lines between what's possible for machines and what's possible for us.
Yeah, it's definitely pushing the boundaries of what we thought robots could do. And who knows what the future holds? Maybe one day we'll have robots that can not only perform tasks, but can actually understand our needs and anticipate our desires.
Robots that can not only work for us, but can actually work with us as true partners.
Exactly. Now that's a future I'm excited to see.
Well, on that note, I think it's time to wrap up this deep dive into the world of EnerVerse. It's been an absolutely fascinating conversation.
It has. Thanks for having me.
A huge thank you to our listeners for joining us on this journey of discovery. We hope you found it as mind-blowing as we did. Be sure to check out the show notes for a link to the full research paper if you want to explore this topic even further. And until next time, keep exploring, keep questioning, and keep diving deep into the fascinating world of science and technology. This is The Deep Dive, signing off.